everyone. In this lecture, we are going to again discuss the pyrolysis process, the mechanism of pyrolysis, but this time that of aromatic solid hydrocarbons. And also the ones that are used in their pure forms and not as mixtures. So for example, petroleum pitches, they are carbonized, but they are hydrocarbons. They also contain a lot of aromatic hydrocarbon compounds, but these are mixtures of aromatic compounds. We are now going to talk about pure polymers. For example, polyvinyl chloride that can give you graphite or graphitizing carbon, or phenol-formaldehyde resins, which are going to give you glass-like carbon. So these kind of pure polymers, when we know the properties, these are well-defined polymers, and we also know the properties or what to expect, in the carbon that comes out of these polymers. So let's talk about the mechanism of these. I do, however, recommend that you go through the lecture on pyrolysis of gaseous hydrocarbons, because there's one important concept of the enthalpy of formation of certain, especially that of light hydrocarbons. That's very important, remains important also here, because in the case of gaseous hydrocarbon pyrolysis, we were more concerned about when will this light hydrocarbon decompose, for example, methane. But now we are concerned about when within which temperature range methane formation is highly likely, because of the fact that it is a very stable, organic compound. So I will say that please do also go through the other lecture. Let's talk about the solid polymers now. Okay, so what do we use them for? You already know that we use them for making graphite, for glass-like carbon, also porous carbons from cellulosic materials. And then these porous carbons are further activated using chemical or physical activation, and then they are converted into activated carbons. So these are the applications. Okay, what else? We also make carbon fibers. Carbon fiber, we are going to have a few lectures on carbon fibers. We are going to have a separate section there. We will also discuss the mechanism of those polymers which are used specifically for making fibers. But the idea is still the same. We make fibers using polymers, and then we convert them into carbon. Okay. Now also we make micro and nanoscale devices. Here what we use is photosensitive polymers, because in the case of micro nano fabrication you need to use certain lithographic techniques for patterning for your manufacturing, and these lithographic techniques utilize photoresist, which are nothing but the similar type of resins. So for example, phenol-formaldehyde resin that has been used for making glass-like carbon for a very long time. But now if you also induce some photosensitivity to it, how do you induce photosensitivity? Either by adding some materials known as photoinitiators. So these are basically additives, and or you can also induce a certain functional group into your polymer which is photosensitive. Okay, or you can use, of course, the combination of both of these things. So that is how you make the polymer photosensitive. However, the important thing is that when it comes to their pyrolysis, when it comes to their thermal decomposition, that depends not on the photoinitiator, but on the skeleton, on your primary polymeric structure. So actually the byproducts that you get from the pyrolysis of phenol-formaldehyde resin at large scale, if you use same or very similar resin at small scale with the photoinitiator, still the pyrolysis mechanism will be guided by the chemical structure and not by the photoinitiator structure. Okay, what else? There are also some other applications. Let's see, if we have time, then we might discuss some of these things, because these are very interesting things, and waste treatment is also a very socially relevant topic. Let's see if we can discuss one more thing that I don't think I have mentioned till now: pyrolysis mass spectrometry. This is also one very interesting application of pyrolysis. Mass spectrometry, at least the chemistry students might know that mass spectrometry is performed when we want to analyze a certain molecule. Typically these are heavy molecules, for example heavy hydrocarbons. What do? We somehow let them undergo fragmentation. There can be various methods using which we can fragment these molecules, and obviously there are every molecule has its own unique fragmentation patterns, but they are unique to that molecule. However, by understanding those patterns, we can guess what is the chemical structure, what type of bonding is present in that kind of hydrocarbon. However, now how do we analyze these fragments? So one way of doing that is by measuring their mass. This is what is known as mass spectrometry. Now, in this particular case, in the case of pyrolysis mass spectrometry, what you're doing is you're utilizing the pyrolysis process for the fragmentation of your heavy hydrocarbons. And this kind of technique is used for example, analyzing fossils. Fossils are they do contain organic matter, and also they're extremely valuable. You just find one fossil, you cannot have several grams of it. You find what you find. And also they are, very small quantities are available. They're very valuable materials. So all of these reasons, it's very important that we can just guess their molecular structure using very, very small quantities. There we are making, often we are making a wire, or at least traditionally that is how it was done. You make a metal wire which can be joule heated, coat your metal wire with the with this whatever material you found, and then heat that wire. That material will then pyrolyze, fragment, and then you can analyze the fragmented parts. Okay, fine. So these are some of the applications of the pyrolysis process, pyrolysis of solid polymers. Okay. Now, how do we find out the mechanism of pyrolysis for a certain given material? So what you can do is you can analyze the byproducts. This is what is also the fundamental principle of mass spectrometry and so on. You can analyze the byproducts, and then based on that you can guess what happened. But this is not the only thing. So there is, when we understand the pyrolysis mechanism of a polymer, we need to understand two things. What are the chemical structures that are being formed? So how chemically it is breaking apart. But also we want to know whether it is undergoing coking or charring. So whether it is going through a semi-solid phase or not, because that decides, that determines a lot of things for the type of carbon you obtain. Okay, so one thing you will definitely do is analyze the byproducts. What you'll also do is you will see what kind of pattern you get when you carbonize something. So here I have taken an example of microfabricated carbon structure. Okay, you know that in the case of large structures, you use slightly higher temperature, and in that case also you need to do multiple times, you need to do resin impregnation, for example, to get rid of the porosity. But in the case of micro nanoscale devices, because the structures are extremely small, they offer a very high surface to volume ratio. So the defects as well as byproducts can anneal out easily, and that is why you can work with slightly lower temperatures. Never mind. The point is that one interesting thing that microfabrication also offers is a platform to study the mechanism of pyrolysis. How? Because you can make structures and then see what is their shrinkage pattern, and the shrinkage pattern tells you about coking or charring also. Okay, so in this particular structure that you see here, this is a atomic force microscopy tip that we fabricated on top of a silicon cantilever. So you can see this structure is a silicon cantilever, and then using 2-photon lithography we patterned this tip, the conical shape. Okay, and then this was carbonized at 900 degrees centigrade. And you can, what you can see here, and why I showed this picture here, is that there is a big black circle, if you see in the bottom. So this was the circle, this was the region where we had the polymer tip. And after carbonization we had shrinkage. Now you see it has become so much smaller, which was actually also in the case of microfabrication. This is very useful. You can convert a microscale structure into nanoscale structure by using the idea of shrinkage. But what you can see is that this black footprint actually is the region where your polymer could not have the same shrinkage as it would have in the rest of the structure, because of the fact that it had a good adhesion to the silicon substrate. This tells you that it undergoes coking. Because these kind of patterns would exist mostly for something that undergoes a semi-solid phase. If you had a polymer which undergoes charring, which means it remains rigid, it might even have some softening, but it would still, the skeleton would remain rigid. In that case, you cannot get these kind of shrinkage patterns. You might, in fact, too much shrinkage would cause cracks in these kind of structures. Okay, so in fact, if you remember this particular image of a pillar, I had shown it to you in the very first class when I was telling you the difference between micro scale structures and microstructure. Okay, so in this image, if you see, there's something very interesting. This was, so let me tell you, this was a pillar. We tried making very high pillars, and then because it was too high, it fell. Accidentally it fell, and when we took the pictures of the fallen pillar, Now this was fabricated on top of a silicon wafer, so it had a substrate. There was a boundary condition. So if you know this is your silicon wafer, and then on top of that you have whatever, you have your pillar. So this is how it was. Now when the shrinkage took place during pyrolysis, you see in the bottom of this picture, you can see that there is still certain region where the material could not shrink because of the fact that it was attached to the silicon wafer. And this is how also you can see how you know what are the shrinkage patterns. This is yet another interesting structure. So when we were making these, you know, AFM tips, at that time, initially a lot of optimization was going on because of the fact that this was, you know, a polymer. We did not know much about its chemical structure. So if you purchase a lot of polymers nowadays, especially for lithographic purposes, you may not know all the details of their chemical structure because, you know, these are companies are specially selling their specialized inks, and they have their intellectual property rights protected. We respect that, but we need to find out whether or not the material is useful for carbonization. Okay, so in that case, you need to here and there perform certain trial and error experiments also for when you're fabricating the structure. So we made a tip, and then we placed it like this inside the furnace. What would that do? Well, if the material is going through a liquid-like or semi-solid type of phase, then you will get certain bending, which you can actually clearly see in this structure. And what is the solution to that? Well, next time you place it like this inside your furnace. So in that case, of course, there has to be some support where so the tip is not broken. But the point is that in that case, you can you know, you need to optimize the shapes for every single polymer that you work with. You will play with all these parameters to find out whether or not your material goes through undergoes coking. So this is how we come up with some mechanism of pyrolysis. Okay, now let's see some examples. So the first example we have here is that of phenol-formaldehyde resin. Phenol-formaldehyde resin, why? Because they are very common precursors for glass-like carbons, micro scale as well as large industrial scale. Remember that phenol-formaldehyde resin is not just one chemical compound. It is a class of compounds. So you basically have phenol and formaldehyde, and you mix them together and you get these kind of resins. However, you can have different ratios of phenol and formaldehyde. You can also have certain functional groups. You can also, for example, induce epoxy group. These functional groups will also slightly change your pyrolysis mechanism. But you know, some basic compounds are often found in the pyrolysis of phenol-formaldehyde resins. So when you analyze the pyrolysis product, and this is what I'm going to show here. So you see there are a lot of chemical reactions here, and I have taken some of them from certain books which I will cite at the end of this lecture. You see that you have a phenol structure and you have a formaldehyde molecule, and then you add these two together, and then you will get certain water will come out and alcohol will come out as byproduct. Now once you heat, so here you see there is also a temperature axis. This is where I've shown the pyrolysis temperature. Okay, and you also see that we are only talking about the region which is, you know, within 600 degrees centigrade, because this is the region 600, 700 where you have most of the important chemical reactions or fragmentation reactions taking place. After that, you basically lose hydrogen, and then at some point carbon-carbon bond formation starts, or pretty much starts also at the same time. But the chemical reactions when you're losing non-carbon atoms, this is what is happening during your pyrolysis region. Okay, so if you increase the temperature now, from room temperature, let's say you go to 200 degrees, and then you go to 300. Let's see, these are some of the compounds that have been found in the analysis of the pyrolysis product during the analysis. Okay, so you can see that it's not that there is just one type of molecule. You will get different types of molecules, but these are some of the primary products. Okay, as you keep on increasing the temperature, then you see there are different chemical structures that also can be, they are all connected with each other as well. These reactions are some of them are also secondary reactions. And you also see what is very important is that you have water molecules being produced. You also have methane and carbon monoxide being produced. Remember that carbon monoxide, carbon dioxide, these are also methane. These are very stable hydrocarbons. So whenever they get a chance, they will be formed. And when I say they are stable, that means they have a very negative enthalpy of formation. So this is also very important for us to understand. But you will see that also hydrogen being produced, all of these gases, then you will find in your synthetic gas that comes out of pyrolysis of phenol-formaldehyde resin, and in the tarry byproduct, you can find some of these chemical structures which do not undergo secondary reactions, and they are volatile, so they just escape the material. Now, some of them will also be mixed inside your synthetic gas if they are very volatile, and if they're not so volatile but they do not want to undergo secondary reactions and so on, then you will find them in your tars. So tar is basically this mixture of a lot of different small hydrocarbons, also small but not too small. Okay, so this is phenol formaldehyde resin. What do we use it for? For making glass-like carbon. And the photosensitive ones are used for in photolithography, and that you can use for microfabrication using glass-like carbon. Second example is that of polyfurfural alcohol. So this is a type of furan resin. Furan is basically this ring which contains oxygen. Okay. Here also I have shown the pyrolysis temperature, and you can see now here I've made these different steps where which gaseous product is most prominent at which pyrolysis temperature. You can also see what happens above 490 degrees. So these things, so here I have only shown it up to 490 just because of the lack of space. Then I went down here. So you can see these reactions take place below 490 degrees. This again can be 500. 490 is not the exact, again depending upon the furan resin structure, the polyfurfural alcohol. They do have very well defined structures, but still the variation can be there, slight variation can be there. But let's say above 490, then you get these kind of compounds. Okay, so this is the standard fragmentation pattern for a furfural alcohol. Again, what do we use it for? This is also a precursor for glass-like carbon. And this is relatively inexpensive compared to phenol formaldehyde resins. So we utilize that. Now you will see that during the initial pyrolysis, you do have a lot of weight loss in the case of furfural alcohol. So you see that there are a lot of gaseous products being released from this kind of chemical molecules. Okay. Now let us also talk about pyrolysis of naphthalene. So naphthalene it's not a resin, it's not a polymer. It's just an organic material, and at room temperature it's solid form. Why did I choose the example of naphthalene? Because there is something very interesting about it. Okay, number one, it's a very simple molecule. You can see that this is one of the simplest, bicyclic structures. And so this is a very simple molecule, so it's easy for us to understand. Also, we can predict, theoretically predict a lot of chemicals that might be produced, when you heat treat naphthalene. But when you actually perform the pyrolysis, it has also shown to yield some fullerene molecules, completely spherical Buckminster fullerene-like molecules. So here you can already see when you pyrolyze your naphthalene, what happens is you are getting cyclic structures, but you also get these 5-membered rings. So here and there you have structures, not all of them by the way. Some of them are also very highly planar kind of structures, but some of them will contain non-6-membered rings, especially 5-membered rings. So they do have a tendency to bend. And when you have massive sheets of such structures where you have here and there 5 or 7-membered rings and there is a possible bending, and what do you get? This is your curved carbon structure. And when you get massive sheets of curved carbon structures, often you may also end up getting Buckminster fullerene or structures that have very high curvature, even if they are not completely closed. So the pyrolysis of naphthalene has actually been reported to yield fullerene structures. So this is yet another example. Now we'll take also another similar example. So this is the example of polyphenol. Okay. Again, this is not a heavy hydrocarbon. That is why I said similar example, because this is not an example of it's not a very complex molecule. But again, you have these structures. So there is a certain cyclization that is taking place. And what is happening above 700, also you can see that now you're getting large sheets of aromatic carbon. And these kind of then polymers can actually yield very good graphitic carbon. Okay, so this chemical has not been reported. At least I could not find any paper where they say that you will have fullerenes being formed or curved carbons. I also don't see any 5-membered rings, but you can try it out and see what what do you get. Okay. So now coming to the characterization of the pyrolysis products, I told you that all of these things we have decided based on the characterization of your byproducts. So what are the at what stage, what kind of characterization technique will you use? That is very important. So that is why if you are given an unknown polymer, or you know very little about it, or you don't have complete information about it, then what do you do? How do you find out what is going to happen? So number one, you will one good idea is to make small scale structures, and then see the shrinkage patterns, especially if you have it attached to a substrate. That will give you the very first idea of whether or not it is undergoing coking, so whether or not you're going to get glass-like carbon from it, or graphite-like carbon from it, or it is undergoing charring. Most of the synthetic polymers would typically undergo coking, as a rule of thumb. So, but still, that is something that is your first, experiment. But then you now want to understand or analyze the byproduct of pyrolysis. Okay, so here is I've prepared a chart where I show what techniques can be used. This is not, you can also have some other advanced techniques, but these are some often used techniques for so generally used techniques. Okay, so you pyrolyze your polymer up to 700, let's say. So we are not talking about very high temperatures, huh? Okay, what do you get? You get synthetic gas, you get pyrolysis oil or the tarry product, and then you get some solid product. Especially if you have performed this process under nitrogen or under a strictly inert environment. In that case, you will often get a lot of solid residue. If there is any combustion also taking place in the process, then you will not get, then you will get a smaller fraction of the residue, solid residue. Okay, now what is important for us? All of these things. So you need to analyze also the gases, stars, and you can also, now what do you do with the residue? First, let's complete the chart here. What do you do with this residue at 700 or at this temperature? You don't have carbon yet. So what you have is, it's or if you call it carbon, then it has a lot of impurities, because it also has these hydrocarbon impurities still mixed. So what you can do is you can fractionalize this residue. So you can basically now separate out the soluble products or soluble chemicals from that thing and insoluble ones. So this is going to be a simple fractionalization or simple separation, because you can actually try, you take this pyrolysis residue and you try to dissolve it into as many organic solvents as possible. Why organic solvents? Because typically all of these are organic, tar-like materials. So they're soluble only in organic solvents. Polar, non-polar, you can try both. And then what you can do is, after you have, so the soluble things will be in the solvent, they will come out, and then you still have some insoluble pyrolysis residue, which most likely contains all of your carbon. Because carbon is typically insoluble in everything. So it's the hydrocarbons that will be soluble. What do you do with this insoluble residue? Then you further heat treat it. Then if you want to get graphite, you can go for graphitization temperatures, or if you want to stop at a certain temperature, let's say 900 or 1500 or whatever, then you heat treat this residue, now the insoluble part, at further heat further temperatures. And at the end, again, you will still, because there will be some non-carbon entities, maybe there's still some hydrogen left over, so you'll get some gaseous product, and then you will get carbon. If you want to go for graphitization, then this carbon also in a way further processed, and then you want to decrease the despacing. Okay, so this is basically what the entire chart of pyrolysis. Now coming to the characterization technique at each step. Okay, so when you're performing the pyrolysis itself, what you can do is something known as thermogravimetric analysis. We are going to discuss all the characterization techniques. When you perform, this is commonly known as TGA. So if you perform TGA, you're basically looking at the weight loss. Weight loss gives you a lot of information about what is happening to your material. So that you can do gas chromatography. So similar to mass spectrometry, this is basically what you're doing in gas chromatography is basically you're analyzing again the fragments of your the fragmented molecules or whatever came out after the fragmentation of your heavy hydrocarbon. You can analyze them using gas chromatography or mass spectrometry. There can be also some other methods, but these are commonly used methods. So this is what you do at the pyrolysis stage. Okay. Now, when you have the synthetic gas and pyrolysis and the pyrolysis oil, the tar-like materials, you can also, of course, you analyze them again using gas chromatography, mass spectrometry, and also various types of molecular spectroscopy techniques. For example, you can use infrared spectroscopy and so on. Okay. Also, for the pyrolysis oils, you can use very similar techniques. So here, rather than gas chromatography, you will use mass spectrometry, and you can also use various chemical analysis techniques. Okay. Now, for the solid residue that you further processed, what you can also do is, at that point, you can do certain analysis. So whether you can dissolve it into a solvent and then take the fraction which has all the hydrocarbons dissolved into it, and then you can analyze it. That can be analyzed using various techniques, or you can, even before that, just the residue itself, you can measure the porosity of that residue. You can also, you have some carbon in it, and you already have some sheet-like structures, because you see that cyclization does take place before 700 as well, or around 700. So you will have some sheet-like structures. That can be, the d-spacing can be analyzed for them. Of course, that will be higher than that of carbons, that of graphite for sure, but you can measure it to understand how much higher is it, what is the d-spacing value. You can also do Raman spectroscopy at this point. Maybe you will get a very complicated spectrum, but these are the techniques you can do. Various you can use electron microscopy, optical microscopy. Of course, you can do elemental analysis. Actually, elemental analysis becomes very important at this stage, which is a simple technique. Often you will use carbon, hydrogen, oxygen, nitrogen analysis. That is also available rather easily. Now you can understand whether you have 90% carbon, 95, 98. So whatever other techniques, yeah, electron spin resonance is also a very interesting technique, where you can find out what the nature of the radicals that are present inside your material. So all of these, diamagnetic susceptibility is often used for understanding the d-spacing of carbon materials. So you can use all of these techniques for analysis. Also, now for the soluble the part that I was discussing before, there you can do a lot of things. You can do fractionalization, boiling analysis. You can use TLC, thin film chromatography, and see, you can separate, because once you have liquids dissolved in some organic materials dissolved inside a liquid, then it becomes much easier to perform. You can even perform NMR, of course, ESR again, and you can also then perform X-ray diffraction analysis, which you can also perform X-ray spectroscopy rather, and also for the surface analysis for fractionalized pyrolysis residue, you can also use XPS, which is known as X-ray photoelectron spectroscopy. That gives you details about the surface functional groups. So these are the techniques that then you can utilize at these stages. Once you have heat-treated carbon, then X-ray diffraction is the most common technique. You want to know the d-spacing, and that is why you use X-ray spectroscopy. Raman spectroscopy now will give you a good value of the disordered and graphitic content in your carbon. You can, of course, use electron microscopy. TEM nowadays has become very, very common. You can still use TGA if you want to still see, what is the weight loss because of the loss of hydrogen, if you had any. So you can still perform TGA at this stage. And finally, for your final products, the carbon, again, BET is a surface porosity, a surface area measurement technique. You can do all of these techniques again and analyze the gaseous and pyrolysis products. So you can also have any other technique. For example, for measuring porosity, there are many new advanced techniques nowadays. You can perform, tomography and so on. You can use various other techniques as well, but the idea is that these are the stages at which you will analyze your different pyrolysis products, and that is how you will come up with the mechanism of pyrolysis for a given polymer. Okay, so finally, what are the parameters that influence your pyrolysis process, and why do we need that? Because this is very important for us. This is what will determine the microstructure of the final carbon product that we are going to get. Okay, so some of these parameters, the important parameters, of course, one thing is the temperature. The temperature of pyrolysis and the temperature of overall heat treatment. Both are very important. So even if you're getting, for example, the graphitizing carbon from a certain polymer, still whether or not you will get graphite, that will depend on your, the further steps of your heat treatment. So the entire heat treatment process and the temperature of everything is very important, right? Okay. The temperature ramp rate is also very important. What is temperature ramp rate? That basically tells you how fast you're increasing your, or how fast or how slow you're increasing your temperature. So 5 degrees centigrade per minute or 25 degrees centigrade per minute will make a lot of difference. If the pyrolysis process is very fast, in that case, you're not providing enough time to your byproducts to anneal out or to gaseous products. So they will then end up participating in the secondary reactions, or they may end up redepositing on top of your material. In fact, if you perform pyrolysis inside a closed container or open container, even that makes a lot of difference, because there is this redeposition or reparticipation of the byproducts in your reaction. So all of these things will definitely make a difference. The dimensions of your structure, so various, now multiple times we have talked about whether you have small, when you have very small structures, let's say smaller than 20 nanometers, then they may graphitize even at very low temperature. So the idea of because this depends on various factors, the fact that okay, one is the annealing out of the defects as well as byproducts, also the idea that the voids cannot really be accommodated in a very small scale structure. So the voids will have no other option but to anneal out. So that is because of these reasons, the structural dimensions make a lot of difference. And this is also important for us because nowadays we are working in the nanoscale, often working in the nanoscale. So some of the principles of the bulk pyrolysis or bulk industrial fabrication of or manufacturing of carbon materials may not be, they cannot be directly translated to nanoscale because the structural dimension changes. So this is an important factor. The residence time, that is the dwell time, also it is called commonly, is the time when you, at the highest pyrolysis temperature or highest heat treatment temperature, for how long do you keep your material? That is the residence time. This is important. What else? Cooling rate. We have not talked about cooling rate, but also, okay, most of the lab scale furnaces may not even allow for, control on the cooling rate, but large, massive industrial furnaces definitely allow. They allow for, they facilitate water cooling, for example. Then you can also set the cooling rate. And that also makes a difference to the microstructure of your carbon. Mechanical forces. So here I'm specifically talking about the mechanical forces that we apply using during the fabrication. So if you're, for example, pulling fibers and you use a rotating drum collector during electrospinning, this you will learn in the electrospinning lecture. In that case, you will have these more aligned polymer chains to start with. So this also makes a difference to the microstructure of carbon. But since we are talking about pyrolysis here, even during pyrolysis, if you place a certain weight on top of your carbonizing material, in that case also that can lead to certain chain alignments, and that can give you a slightly different microstructure than what you expect. Okay, chemical structure of precursor, of course, this is the most important thing. That depends upon the structure, your molecule, your precursor, what are you going to get. So this has been then further divided. There are different types of carbon precursors. Some of them contain oxygen. For example, the examples that we discussed today. Some of them contain nitrogen. Then the nitrogen can also be either aliphatic nitrogen or aromatic nitrogen. So one good example of aliphatic nitrogen containing polymers, polyacrylonitrile, again, that is used for making carbon fibers, and we will separately discuss it during our fiber classes. Halogen containing polymers and also sulfur containing. So all of them can have slightly different pyrolysis mechanisms, and accordingly you will get slightly different microstructure in your carbon. The environment in which you perform your pyrolysis, so you will often perform it in the inert environment under nitrogen, but you can also use forming gas. So you have 5% hydrogen mixed into it, or you can perform the pyrolysis also under vacuum. So the environment in which it is performed also makes a difference, because that makes the two things. One, of course, it can induce certain chemical reactions, provide a reducing environment, so that will probably change slightly the byproducts that were being formed. So inert atmosphere versus reducing atmosphere can have slight differences in the reaction mechanism. Also, if you're performing it under vacuum, maybe your byproducts are getting more easily sucked inside. So these things will also make a difference. Okay. The pre-processing or stabilization of the polymers, that is in some cases it is required. For example, for polyacrylonitrile you need to do some pre-processing. Many other polymers require some sort of even pitch is not just polymers, you need to do some pre-treatment for stabilization, and then the conditions that are used for stabilization also become very important. Okay, pressure, well, we haven't again talked about the pressure induced pyrolysis, but if you have so you have an autoclave process, so you have certain induced pressure during your pyrolysis, in that case that can also influence the microstructure of your carbon that you get. Additives, catalysts will definitely make a lot of difference. You know that how do we get graphite using metal carbides. So these, even in the case of chemical vapor deposition that we will talk about during nanomaterials, catalysts make a lot of difference. And they influence the they very strongly influence the formation of carbon structure, so the type of carbon that you get from that. Okay, finally the mechanism of pyrolysis, that is the most important thing. Coking and charring, we have been discussing that. So these are all the parameters. Maybe there are some more, but these are the primary parameters that will influence your pyrolysis process, the mechanism, and accordingly the microstructure of the final carbon material. Okay, one very important thing that you must remember is that whenever a polymer is undergoing charring, you will never get graphite. You will predominantly get hard carbons, or what is known as non-graphitizing carbons. By the way, non-graphitizing carbons are also known as hard carbons because they are hard and brittle. And graphite-like carbons, although sometimes they can also be hard, but often they are called soft carbons because they have this layered structure. So you can get soft carbons, you will typically get, or graphitic carbons you will only get when there is a coking mechanism. However, coking does not always give graphite. So sometimes you'll have graphitizing carbon, sometimes you'll have non-graphitizing carbon, but charring will always give non-graphitizing carbon. So this is something very important. Now, how does coking help in yielding graphite-like structures? Well, coking enables the migration of your graphene-like sheets, graphenic sheets, which are being formed during the initial stages. Or even cyclic structures, polymeric cyclic structures. They are not necessarily, they still contain hydrogen, so you don't call them graphene yet, but these cyclic, large-scale cyclic structures, they can easily float if you have this coking mechanism. And that is why this is very important for if you want to get graphite-like structures, then you need to have sheets organized on top of each other. That is when you will get good stacking. Even in the case of glass-like carbon, you do have, these are non-graphitizing carbons, they contain a lot of curved carbons, but even in that case, the dissociation of these fragments from larger fragments, and then they float and then they migrate and attach to some other, so they are able to form more stable geometries in a more convenient fashion if you have a fluid-like or liquid-like or semi-solid-like structure during their carbonization. So coking is very important for giving any carbon with flat and shiny surface, of course, and any graphitic carbon. Charring, well, you can have, if you keep on increasing the pyrolysis temperature or the heat treatment temperature, at some point you will get some short range order, but compared to carbons that are prepared by coking, that is not going to be as good. Or the electrical conductivity is not going to be as high. So these are some very important parameters. So also to show you how does this work with the coking and coking mechanism, the sheets can actually align on top of each other if they are, or in the case of charring, that will not happen. If there are two sheets next to each other, there is little possibility that they can place themselves on top of each other. So this is for you to think which of these structures is better in terms of graphitization, or which of them enables more interaction between the two sheets. It's very clear, but this is for you to think. Okay. So now for further reading. So I already told you that you must look at the lecture on non-graphitizing carbon in the gas phase pyrolysis. Maybe some other lectures as well. These are two books from where I have taken some of these diagrams, especially the diagrams on the phenol-formaldehyde resin and furan resin fragmentation patterns. Okay, so these books you can also use for further reading.